So my name is Jaebum Jung, and I'm the kernel developer working at the Wolfram Research. And my talk title is 3D printing. It's basically talking about how to use the Mathematica, the 3D printing with Mathematica. So that's the general topic of mine. So this is like the general flow of 3D printing. So first step you need to do, you need to get some model. So there are various ways to get model into Mathematica, like access to repository that's the curated data. So there are many data set in Mathematica you can get freely. And also you can use import functions to import any 3D data out there. And also you can just create models in Mathematica with some Mathematica functions. After you get model, next step will be the analysis. What it means is you need to check the model is actually good enough to print out. And also you can get to know some properties of your model before you print, like estimate the price or how big it is, something like that. Also for engineer aspect, you can check if your resulting model has some weakness or not. After that, last stage is production, actually print. So there are 3 different ways we categorize that way, like using the 3D printer, local 3D printing at your home. And also you can send your model to online printing service, or you can just create the 3D format, the file, like a STL, OBJ. So let's get into little details. So here's some ready-made 3D printable model. So this basically is from the Mathematica, the data. So this first one, it's kind of small. It's from anatomy data, so you can use the entity, or you can say anatomy data skull, comma, lesion, you will get this result. Let me see. Oops. Okay. So let me get to the slide. Where is it? Okay. And this one is not data. And so we adding almost to every the data that previously graphics, we add a new property called lesion. So it's not just discretizing, using the discretizing graphic. We actually fine-tuning the actual mesh. So this mesh that getting from comma lesion should be good to print. And here's the chemical data. This is one that we did the effort. So for example, like here, you will see currently, if you get just graphics, and do the discretized graphics, then you don't. Oh, graphics 3D, yeah. What? So it should be good. It should be graphics, I missed. Let me just double check, I just sometimes too many. Oh, molecule flat, that's, yeah. But okay, molecule flat. Okay, let me pass that. So you molecular plot, if you use that, you can get graphics 3D. And then you can apply discretized graphics, but that will not giving the same result you get here. So this one is fine-tune the mesh region, which works well with 3D printing. And here's another one. geo-elevation data. And this is a new type, the legend. So it's giving you elevation data. And this one is what you see right now. But we have something new. This one. Where can I just? Okay, so let me. Sorry about this. Okay, something's messed up. Sorry about this. Yeah, from now. Oh, so everything's messed up now. Okay, I just gonna say. So dear, you see the resolution is not so great right now, but the coming version of Mathematica. Tomorrow, great. Yeah, so tomorrow you get a much better resolution of this one. This one doesn't look like Mount Everest, but new version, it really looks like some mountain, and you get much better resolution. That's good to know. Okay. So, and then, what happened? Okay, so something's wrong. It seems like, okay, here we go. And then there are another data like solid data, region. This doesn't giving actual the mesh region, but it giving some function. What it means is you can apply the parameter here, and then this create a region that you get actual region. So it's slightly different type of region, but also you can see some printable data. Let me see why, I don't know why it's crashing. Okay, it's broken in some sense. I have some bad corner right now. So that is the another example. So here another way is importing 3D models. So this is supported 3D graphic, the type, format, STL, PLY, OBJ. And this looks same old one, but in new version, what we improve the performance of STL and OBJ, the 3D importing functions. So for example, like if you see one of the marketing page, let me just, so this is time comparison. So for large mesh, it improved like more than 100 times faster than before. That's what we have in new version of Mathematica. And another way is using the 3D plot functions. So what you see is, in general, if you just print out, for example, like without the plotting, let me see. So this is what you see. If you see it, you see the surface actually thin paper thin. So in this case, if you just try to print this the graphics, it doesn't really work well because it's just thin, tiny thin. So we're adding some new plotting called like thick surface. What it does is it actually giving thickness automatically to your plot. So you can, now it's a printable model here. And another, let me just, okay, here it works. So another, the plot theme we have here is field surface. What it does is actually just making bottom base. So it's also making the printable function. So if you remove this one, you will see it's also paper thin. And if you plug in this to printer, then printer will complain about it. Let me just keep corner. Which one? The previous thing. This is a plotting for the 3D plots. So it's only works with the plot functions. And algorithmically generate 3D model, what does it mean is, you applying sequence of functions, mathematical functions, and then create some 3D printable object. For example, we have image, and then you do some image processing, color negate, it's just changing black to white, white to black. After that, we have function called image mesh, which actually converting the image to mesh. And we do operation region product with line. So this is actually extrusion. But usually if you do the extrusion with just graphics, it is not that easy. You have to do the many computation. But here's just region product. It makes sense, image with line that is giving kind of cylinder shape, 3D shape here. And this definitely printable.
What's the geometry of the mesh? Is it triangular or rectangular?
In here?
Yes.
Yeah, you can see easily. So, oops. Let me see. Oh yeah, I didn't evaluate this one, so that's why. Sorry. So it's triangle with, see, and then the actual, this part is the rectangle. So it's a mix of triangle and rectangle in this case. Okay, where I am. Okay, here we go. And another thing, after you get the model, you want to do some analysis. So here's some basic example doing analysis. So you get the model from example data, so it's a famous space shuttle. After that, you can easily compute the volume of this region. And then, so you get the density of aluminum. This is possible because we now have like Wolfram alpha access and entity. And then compute the area and estimate some price. So this is just simple example to series of operation you can do with mesh. And now, so to find out the mesh is actually the good mesh to print out, we have a new function called find mesh defect and then repair mesh. So this is a list of defects you can find with Mathematica. So we kind of categorize some popular defect. Popular doesn't really sound good, but here we have edge detection and T-junction, overlapping faces, dangling edges, and singular vertices, flipping faces, so etc. So usage of this is very easy. Okay, let me see. So you just do find. Oh no, it comes out. I don't know why. So basically, just find the mesh defect and then put the mesh. And it try to detect every defect that I just show you, and then visualize it. So flipping faces, whole edges is all highlighted, and easily you can see what defect you have. And other usages, like you can specify specific defect. So whole edge, then it only show you the whole highlighting. Or if you want to get the cell, you can, using the second argument, cell. This means you actually get the defected cell. In this case, this whole, 1, 2, 3, 4, 5, 6 on the model. And once you find defect, you can now repair it. So again, just use repair mesh and plug in your mesh. Then you can the repair mesh. And then if you want to just remove one defect, you can specify also. Then you see there's still defect here. Only the isolated vertices is removed. And there is another operation you can do using the new function shell region. What it does is, so you have some solid. And if solid, that means if you sending that to printer, you see this slice is all filled. And so most of cases, you don't want to fill. It requires more material, and visually, it doesn't really make any difference. And shell region actually hollow your model, so you got some empty inside. And then if you see this slice, the middle part is empty, so you can reduce the amount of material you use. And if you check the volume of it, it's more than half, reduced more than half. And here's some other example you can do with the Mathematica. So you have a model, and this is function we using the NDSolve FEM finite element package. And this is some operation that actually compute the stress of your model. And you got some parameter you need to plug into the functions using the Wolfram alpha. And you do NDSolve with these tracks. And then there are another function inside that actually showing the stress you just computed by this one. And so before you print, you can check the weakness of your model. So this is what happened inside of the printout 3D. Let me briefly mention. So let me see. So first thing happened in the Mathematica, it discretized it. So if it's graphics 3D, you need to discretize. Main reason is that to find the defect and then repair, you need to have some reasonable mesh region. After that, as you know, you find defect, and then if you find actual defect, then it tries to repair it. After repair, we send it to printer. But before, I didn't put that step, but before you send printer, there are other operations like resizing. If your model is too small or too large, then it automatically resizing to decent size. That's one thing we do. And also, if you specify some unit, it also do some conversion based on your given data. And at the end, it giving the nice summary. And let me see some example here. So for example, this one, if you don't specify anything, it will open send your model to your default previewer. In my case, I setting my default previewer as some POMNAP software here. So this is what you see. And you can also specify default previewer if you want using like a MakerBot. So this is example of calling the MakerBot. So for example, like now it's open up with MakerBot. And another way is sending it to file. So usage is simple. Same thing, model, and you specify the file name with corresponding the STL. In this case, you want to create an STL file. And if you see the summary status is successful, let me just try it. And also here, report, if you see, it's showing every process is OK. So it describes successfully, no defect, is scaling, and then export. And the last one I will show here is sending to online printing service. So what it does is there are the online printing service we support. So iMaterialize, Sculpteo, Shapeway, 3D Hubs. So what it does is same thing, discretize, defect, and then now it's sending it to online printing service. So inside of it, you are not just sending. Each online service have different requirement. Even the file type they support are different. So if you, for example, like specify Sculptio, we check their spec and convert it, if necessary, we convert it to certain format. And also, the service have different unit. So corresponding to that, we make change of model to millimeter or centimeter or whatever needed. So this is one example. So sending it to Sculptio, kind of expensive, and then you just check, and then if you press review and check out, then you can buy it. They will send it to you. So this is how the Printable 3D works in Mathematica. So our goal is to make it easy to print. So even you don't know anything about it, you just plug in model into Printable 3D, then it will automatically work. I mean, I don't say it's the end, because it's ongoing project, and there are still some room to improve, and that's what we are working on. Next version, next coming version, it will be better than now. And there is other talk. For example, meshes from everywhere is tomorrow, and this will talking about more like a discretization process. So that will be good. Also, we have game engine talk tomorrow, which will introduce some Unity integration, not integration, using Mathematica to make some game, something like that. So if you're interested in, it's Friday 4:30 to 5. So that's end of my talk. We have 1 minute if you have any question.